And today we're going to get into circuits. So let's just sort of a quick little recap of what we've been doing. Remember, a capacitor is two metal plates that are parallel to one another. The plates have two dimensions that are associated with them. One is the area of the plates, and then one is how far the plates are separated from one another. And those two dimensions combine to give us the capacitance. And we sort of came up with that expression for the capacitance that is dependent upon the area and the distance between them. The C equals epsilon naught A over D. And then also the capacitance is dependent upon the dielectric that you put in between the two plates. That dielectric is mainly there to keep the two plates from touching, but it also increases the capacitance. And that dielectric constant we call kappa. Now there's another expression that we use to describe the charge on a capacitor. That was this Q equals CV. Those of you in Ohm's law, I like to think of this as like the Ohm's law for capacitors, because it looks sort of like Ohm's law, and it works a lot like Ohm's law. But this tells us the charge on the capacitor is related to the voltage or the potential of the capacitor, and also on the capacity of the object to store charge. A capacitor, that's what it does. It stores charge. It can also store energy, and some of your assignment questions will deal with that, like how much energy is stored. We'll get to that later, maybe not today, but we'll get to it. All right. Now we're going to get to circuits, and we're going to deal with circuits. We're going to be in circuits for a couple of chapters. I think circuits are fun. I think that you'll like circuits. Many of you will like circuits. There are only a few simple rules that guide circuits, and then once you master those rules, it's really sort of like putting together a puzzle. So I find that a lot of students like circuits. I like circuits too. I think that you'll come to enjoy them. First of all, just a few symbols. The symbol that we use for the battery, if you're in the lab, you've seen this symbol. It can have a couple variations. I'll just use a symbol like this, and sometimes I'll write the voltage underneath it, 12 volts. And by the way, when I'm using voltage or potential difference in terms of circuits, usually I'm talking about the same thing, and that is the voltage that the battery provides. You might see some slight variations to this, like sometimes you'll put plus and minus on them along with the number. On a device, usually this is red, and usually this is black. All right? A capacitor, the symbol looks like this. It's just two parallel plates. Be careful though when you're drawing them, because if you draw your lines a little bit differently, it can look like a battery. That's why some people actually use this symbol for capacitors. I won't use it, but some people do, where they use like a straight line and then a curved line. But we'll use this symbol on the left. We'll use this symbol. And then the resistor, we're not going to get to resistors for a while, but resistors look like this. You can also have a variable resistor, which we won't see in this class, but you see it in the lab. A variable resistor looks like this when you just draw an arrow through it. This is a variable resistor. It just means it's a resistance that can change its value. All right. So those are the symbols that we'll see. If you're looking at complex circuits, you'll see a few other symbols, but these are sort of the main ones. If you ever open up the user's guide for like your car stereo or whatever, and they show you the electrical diagram, a lot of your symbols will look like this. Okay, so we can connect devices, whether they're capacitors or resistors, which we'll get to in the next chapter. We can connect them in either series or parallel. And so we're going to treat them separately. First we'll look at capacitors in parallel, then we'll look at capacitors in series, and then we'll put them together in what we call combination circuits, where you have capacitors that are both in series and in parallel in the same circuit. All right, so let's see, for capacitors in parallel, look like this. Like you imagine that you have your battery. This is your battery. You have one capacitor hooked up like that, and then you have another capacitor hooked up like that. This is the same. We could draw this in a similar way and it would be exactly the same as we could have a capacitor hooked up like this and a capacitor hooked up like this. These are the identical circuits. The way that we would draw this as a circuit diagram, I'll draw my battery like this, a capacitor there, and a capacitor there. So those are my two capacitors and my battery. Those are two capacitors in parallel, but of course you can have as many as you want, on and on. Now, when C1 and C2, let's say that this is C1 and this is C2, when those two capacitors are in parallel, they have the same voltage across them. And that's one of the reasons I like drawing it like this, is because if I imagine this battery is hooked up to C2, but it's also hooked up to C1. And it's like both capacitors are hooked up directly to the battery when they're in parallel. So you can think of these as when the capacitors are in parallel, it's like each individual capacitor is hooked up by itself to the battery. So if two capacitors are different, then they have different charges stored within them. We'll do this later, but let's just go ahead and do a quick little thing. So let's say that I have, let's see, I'm just going to do two capacitors here. Let's say that I have two capacitors. Say this is 4 microfarads. And let's say this is 2 microfarads, and they're hooked up to a battery of 12 volts. All right? What is the voltage across the 4 microfarad? It's going to be 12. They have exactly the same voltage as the battery. So I've got 12 volts here, and I've got 12 volts here. Now remember, we have this expression, Q is equal to CV. So if I want to know the charge on either one of these capacitors, I would say the capacitance times the voltage. So the charge on this capacitor is 4 times 12, or 48. And then the charge on this capacitor is, what is that one? 6.1? No, what is the charge on this one? 24. All right, I just say it's the capacitance times the voltage. All right, so each of these has, the one with the bigger capacitance has 48 microcoulombs, and then this one has 24 microcoulombs. Notice how I did that, by the way. I said that Q is equal to 2 microfarads, that's C, times 12 volts. And I could say that this is 2 times 10 to the minus 6, and this is 12, and that gives me 24 times 10 to the minus 6 coulombs. Or I can just sort of carry that micro out. And we'll do that a lot in this chapter and the next chapter, especially this chapter. And we'll just sort of carry this micro. So I say 2 times 12 is 24 microcoulombs, not coulombs. Okay? That's pretty standard. We'll do that a lot. But just sort of be careful with your units as you're going through. So notice the one with the bigger capacitance has the bigger amount of charge. And that might seem obvious, but we'll see some scenarios where that's not true. So that's why I just stated here. So as I said, when electrical devices are connected in parallel, you can imagine that they're connected directly to the battery. I've already drawn that picture. Just imagine in parallel, they're all connected directly to the battery. All right, so what is the charge on C1 and C2? Now just take a moment. I want to know the charge on capacitor 1 and capacitor 2 in this parallel circuit. What is it on C1? 10 what? That's awesome, yeah. So my charge on C1, I'm going to call it Q1, it's C1V1. That's 1 microfarad times 10 volts, because each of these has 10 volts, and so it's 10 microcoulombs. All right, the voltage on each capacitor is 10 volts. Q2 then is going to be C2V2. That's going to be 2 microfarads times 10 volts, or 20 microcoulombs. All right? I know this is new to you now, but as you go through the circuits, it'll become really sort of second nature to you the more you practice circuits. Circuits take a lot of practice because you got to learn to see them in your mind and sometimes sort of think about the different organizations of the devices in your mind. So it'll take a lot of practice. Okay, so we're going to introduce the idea of the equivalent capacitance, and this will come up with resistors too. An equivalent capacitance, if I have 2 or more capacitors, I can replace them with just one capacitor that has the same value, and that's called an equivalent capacitor, or an equivalent capacitance. You know, it says that if I have 2 capacitors in parallel, like these 2 are, that there is an equivalent capacitor that is identical to those 2, where these 2 sets of capacitors are the same. All right, we're going to see this with resistors, and unfortunately, some of you have already seen with these resistors in the lab. Unfortunately, this is slightly different from what we did in the lab with resistors, so you're going to see some flip-flops back and forth between resistors and capacitors. All right, so for capacitors in parallel, the capacitance is given as C1 plus C2 plus C3 plus however many you have. So if I have a 1 microfarad and a 2 microfarad, what is my equivalent capacitance of those 2 capacitors? 3 microfarads, right. 1 plus 2 is 3 microfarads. Okay, let's try this quick test. So this quick test, I want to know what is the charge on the 3 millifarad capacitor. What is the charge on the 3 millifarad capacitor? Emily Throwman well here? Daniel and Daniel and Brody's here. Oh, no. Can you all send that back to Daniel? It'll come back to you, Daniel. The song. Send that back to the song. And Brody, send that. All right, let's stop in a few seconds. I'll stop at 1:30. 1:30. Okay, awesome. So you get the idea with these. Actually, capacitors in parallel are pretty darn simple to deal with, but you'll see 1 or 2 questions for capacitors in parallel. The reason they're simple is because, well, they all have the same potential. And so I have 18 volts here, I have 18 volts here, 18 volts and 18 volts. And then if I want to know the charge on this capacitor, I say Q is equal to C times V. That is 3 millifarads times 18 volts. 3 times 18, that's 30, 24, that's 54 millicoulombs. So 54 millicoulombs. Listen, do y'all know what computers eat for snacks? Microchips. And this isn't a joke, like this is a true thing that's going to happen, but I don't want you to be alarmed. That later in the class, that door is going to open and a disembodied hand is going to reach through the door and deposit something into the classroom. So don't be alarmed when it happens. It might sort of freak you out if you didn't know about it, especially you, Carmen, because you're right there. But just don't be freaked out, okay? It's going to happen, I think. Okay, so capacitors in series are a little more complicated. Capacitors in series all have the same charge. Actually, let me write down the rules that we have, just summarize the rules that we have for capacitors in parallel. For capacitors in parallel, and I'll write these down again, but it helps to sort of write them down and think about them. Capacitors in parallel have the same voltage. Their equivalent capacitance is equal to C1 plus C2 plus C3 plus however many you have. You know, if you go on, if you have 5, it's C1 plus C2 C on up to C5. And Q is equal to CV. I think that's all we have for this. Yeah, so capacitors in series have a similar set of rules. But capacitors in series, they don't have the same voltage. Instead, they have the same charge. So capacitors in series have the same charge. So if I imagine here, let's say that this is my 12-volt battery. Whatever charge I have here, I'm also going to have here. So if I call this Q1 and I call this Q2, then I can say that Q1 is equal to Q2. Another thing about capacitors, we talk about their charge Q. I think I've already mentioned this, but we have a positive charge plus Q here, and that's the charge that we talk about that's on the capacitor. But we also have this other charge. Is this an induced or conductive charge? It's an induced charge. If I get a positive charge over here, then I induce charges here in the middle. Because you notice in these capacitors, this thing in the middle, it doesn't touch anything. It's just sort of like a disembodied hand. It's just out in space. Because it's not touching this plate and it's not touching that plate. It's just sort of sitting there. So I get this induced charge set up on these capacitors where I first put on this positive charge here, and then I get a negative charge there that's equal but opposite. That leaves a positive charge here that's equal but opposite to the negative, and I get the same charge throughout. Okay? So if we were to talk about the net charge on a capacitor, positives and negatives, it would have 0 charge. But what we talk about is the positive charge when we talk about the charge on a capacitor. Okay? All right. So capacitors in series have the same charge. The equivalent capacitance for series is given as this. It's 1 over C1 plus 1 over C2 plus 1 over C3 plus however many capacitors you have. You're going to have to deal with some fractions in this chapter, so if there are only a couple of operations that we'll do, but you might need a little practice just to jog your memory on how to deal with these fractions. Okay, so for example, let's say that we have a 3 and a 6. Well, y'all try it. Try finding the equivalent capacitance of these two capacitors, a 3 and a 6. It's going to look like this. 1 over 3 plus 1 over 6. You don't need your calculators. Just try to do it without your calculators. Honestly, because often I give numbers that work out really easily, and these are nice round numbers. Find your common denominator, add them up, flip it. One-third is equal to 2/6. 1/6. I got it yet? 2, right. Yeah, so you'll see actually that I use common pairs of capacitors and resistors when we get to that. That will add up. And so like the 3 and the 6, that's something that I use a lot. If you look back at old tests, you'll see, gosh, there's that 3 and 6 combo again. And the reason I use it is just because it works out really easily, the math. Sometimes you'll see some that don't, and you might need to use your calculator, but usually I do give you easy ones. So 1 over 3 plus 1 over 6 is equal to 2. That's 2 microfarads. And so that is my equivalent capacitance. that those two circuits are identical. The charge that is found, remember one of our rules is that caps in series have the same charge. So these two capacitors, this capacitor and this capacitor, have the same charge. You follow me? Because they're in series, they have the same charge. It's an induced charge, so they have the identical charge on this one as they do on this one. They're also going to have the same charge as this capacitor. So whatever charge is on the equivalent capacitor will also be on each of those. So let's say that we have, I don't know, 12 volts here. Can you tell me what is the charge on this capacitor? It's not 12. I know with parallel circuits that would be the case. Sorry, I'm not asking for the voltage, I'm asking for the charge. What is the charge on the 3 microfarad capacitor? Well, what is the charge on this capacitor? 24. Q is equal to CV, so this charge is 24 microcoulombs. And since both of these have the same charge, what is the charge on this capacitor? It is 24. Right, so they'll have equal charges that will be the same as the charge on the equivalent. So the charge on the equivalent, Q on the equivalent capacitor, is going to be C equivalent times V. And in this case, that's going to be 2 microfarads times 12 volts. And that's equal to 24 microcoulombs. I'll have 24 also on this one and on this one. Because you know what? Capacitors in series have the same what? Have the same charge. Capacitors in parallel have the same voltage. Capacitors in series have the same charge. So those are two sets of rules that you'll need to think about. Capacitors in series have the same charge. Capacitors in parallel have the same voltage. All right, let's just do an example, and we'll see some other rules that'll come up along the way. All right, so I have this series circuit, and I want to know a couple things about it. I want to know the equivalent capacitance. I want to know the voltage across C1 and C2. And I want to know the charge on all the capacitors. All right, so the first thing I want to do is find the equivalent capacitance. My equivalent capacitance is 1 over 2 plus 1 over 4. That's 4/3 microfarads. Because this is 2/4 plus 1/4, which is 3/4, which is 4/3. If you do it in your calculator, it's like 1.333 or whatever. So the equivalent circuit looks like this. I have 4/3 microfarads. And since the capacitors are in series, they have the same what? They have the same charge. So the charge on this one, which I'm going to call Q equivalent, is equal to C equivalent times V. So that is 4/3 microfarads times 8 volts. What's 8 times 4? 32. So that's 32/3 microcoulombs. So that's the charge on this equivalent capacitor. If you want to go to decimals, that's fine. But now, that's also the charge here. Usually, really what I want to know is I want to know V1 and I want to know V2. All right? Which one's going to have the bigger voltage? C1 or C2, do you think? Some of you say C1. Any of you say C2? Okay, let's look at the Ohm's law for capacitors. That's Q equals CV. If C goes down, that means V goes up. So my smaller capacitors will have the bigger charge when they're in series. Because the charge is constant, this is constant for capacitors in series. If the capacitance is small, that means the voltage is big. It's going to be different for resistors, but for now we're with capacitors. So here I have the small capacitor, I'll have a big voltage. Here I have a bigger capacitor, I'll have a smaller voltage. Because of this sort of inverse relationship between C and V. If one goes up, the others goes down. But I can calculate V. V is equal to Q divided by C. That is 32 thirds divided by 2. Notice that my micros here, they cancel out. So I'm just left with volts. And that's equal to 16 thirds. No, it's not. Yeah, 16 thirds. And then V2, similarly, I can say Q2 over C2. That's equal to 32 thirds over 4. That's microcoulombs over microfarads. That cancels, and that gives me 8 thirds volts. So I want you to note that C1, which is smaller than capacitance, has a bigger voltage. Listen, there's a process that you can go through with all these circuits, and it's kind of an arduous process. But there are also, on most of the questions that I'll give you on the test, there is a way that you can just look at the circuits and think about their relative sizes with respect to one another, and you don't even have to put your pen to the paper. You can just say, oh, the answer is this. And being able to know these relationships, these little relationships, such as when my capacitance is smaller, I have a bigger voltage, that will really help you as you go into the test to get those with confidence and without much effort. That you don't have to actually go through this process of, okay, what is the equivalent capacitance? What is the charge on the equivalent capacitance? Okay, now what is the voltage on C1 and what is the charge on C2? You don't have to go through all those steps. And we'll see that as you go on, that you'll see that there's an easy way and there's a hard way to work through problems. And you can do either. I mean, some of you will do both. But the easier way is, well, it's easier. So it doesn't require as much time. Okay, so also when electrical devices are in series, the sum of their potentials, I think it goes on the next page, I was going to go here, or the sum of their voltages is equal to the battery, or equal to the source. What was our battery in this case? How many volts was it? It was 8 volts. Notice that if I add 16 and 8 thirds, that's 24 thirds, which is equivalent to what? 8 volts. So notice in this circuit, and this will be true for resistors too, that if I have, let's see, small capacitors carry big voltages, so this is 16 thirds volts, this is 8 thirds volts, they add up to equal 8 volts, which is what I have in the battery. So there are often little checks that you can do on circuits to see, okay, does this all consistent with what I expect it to be? All right. Let's not do this one right now. Yeah, let's go ahead and do this quick test, and then I have a video I want to show you. Oh my gosh, did y'all just see that? It was a disembodied hand. Carmen, are you okay? Did it try to grab you or anything? Wow. Huh? I don't know. It's a bag. We should call the Department of Homeland Security or something. All right. What is the potential across the 24 microfarad capacitor? Now you might be able to just look at this and guess what the value should be. I think you probably can actually. You can probably guess correctly. But your steps on this is if you want to go through all the steps, you'll find in your calculator, is you find the equivalent capacitance, you find the equivalent charge on that capacitor, and then you know that charge is the same on all four capacitors. And so when you get the charge on this capacitor, you can find its voltage, because voltage is Q over C. Now follow me? You want to first find your equivalent capacitance, that's that 1 over 1 over business. Then find your equivalent charge. Q is equal to that equivalent capacitance times the voltage. And then, once you find the equivalent charge that's the same on all four capacitors, you can find the voltage across that one. Or if you're feeling clever, just guess and see if you get it right, because you might if you sort of see how the numbers fall. Alright, I'm not sure how many folks we have here. Yep, still working, yes? Still working. Feel free to share your answer with your neighbor. Alright, I'm going to stop at 305. Just guess if you're not sure. 305. Hey, look at y'all. Y'all are awesome. You know what? You could have just looked at this and you said, gosh, that 24 is a lot bigger than all the other capacitors. And I know that big capacitors have a small voltage. I also know that the sum of the four voltages has to add up to equal to 18. So right away I can get rid of A and B, because this can't have either 29 volts or 18 volts, because all four voltages have to add up to equal to 18. And then, you know, it could be either one of these, but since this is such a big capacitor compared to the others, I would bet pretty certainly that it's going to be C. Right, but you want to make sure. So this is how you go through on a problem like this, where the numbers don't work out exactly right. They're not very easy to do. First, you find the equivalent capacitance. That's 1 over 3 plus 1 over 6 plus 1 over 12 plus 1 over 24. And does anybody know what this is? 24 over 15, which is what? 1.6? That's 1.6 microfarads. And then you find the equivalent charge. That's 1.6 microfarads times 18. Goodness bless you. And that's equal to 28? 28.8. Sounds right. So that's the charge on the equivalent capacitor. It's also the charge on each of these. It's on all of them, right? Because capacitors in series have the same charge. Capacitors in parallel have the same voltage. Capacitors in series have the same charge. All right, now we want to know the voltage. V is Q divided by C. So we say 28.8 divided by 24 This is in microcoulombs, microfarads. The micros cancel, and that's 1.2. So you probably could have guessed that just based on the information you had about the circuit if you knew these various relationships. But that's the steps that you would go through for a series circuit to find the voltage. All right, I have a video I want to show you. It's about capacitors. I wanted to show it to you last time, but you know, what's he gonna do? This guy, Colin, like he's my hero. When I grow up, I want to be like this fella because he's really cool. But we probably won't watch the whole thing. But he talks about capacitors for exams. I just want to make sure that we get these before we go on to combination circuits. So for capacitors in series, you have these written down, but I find it's helpful to write them again. Capacitors in series have the same charge. Their equivalent is this 1 over C1 plus 1 over C2, and Q equals CV. For capacitors in parallel, they have the same voltage. The equivalent is C1 plus C2, and again, Q equals CV. See, just three simple rules for each of them, and they sort of parallel one another. They're opposites of one another in a lot of ways. These two equations are on your equation sheet, so if you forget those, which you're not, because we're going to use them a lot, you can find them there. And then once you know those rules, the circuits, they all follow those simple rules. Now you'll see next time when we get into combination circuits that it's not always that simple. That when we get circuits that are both in series and in parallel, that they can get a little bit complicated. But we'll work on that. We'll do lots of practice next time. You already have, as I said, your tutor assignment is up. It's due next Wednesday. And you can probably answer most of those today. Now I'm going to hand back your test. Please stop this video.